All right, Dan. Well, if you want to start, you can go ahead and take it away.
Okay. Thanks for tuning in. So today I'm going to talk to you about teaching an old spacecraft new tricks, rolling over MRO to boost SHARAD signals. When we bandied this title about previously, some of our folks at MRO that manage the project were a little disturbed by this use of the word old. And I guess I have to agree. I don't like it when people refer to me as old, so we'll just refer to it as a veteran spacecraft. That's okay with you. So before I get into it, I wanted to thank my co-authors on the paper describing these results who are listed here. A number of these folks are with PSI, but there's others from the Smithsonian, as well as our Italian colleagues from various institutions in Italy. And of course, we have to thank NASA and the Italian Space Agency, OSI, for keeping the MRO project going. And of course, our other friends on the SHARAD team. So I'm going to talk first about a little bit of an overview on MRO and SHARAD to give those who are not as familiar with it as we are a little more background on that topic. And then I'll get into the spacecraft modeling and the rolled observations that we acquire with MRO and SHARAD. Then I'll wrap up with some conclusions and talk about our future plans for this maneuver. So MRO has been in orbit at Mars for over 19 years now. We're actually coming up on the 20th anniversary of the launch, which was in mid-August of 2006 or 2005. So that 20th anniversary is next month. Despite that, the spacecraft is in great shape. All of the instruments are functional. CRISM has been shut off due to budget constraints. It did lose its coolers, which made its high resolution imaging no longer working. SHARAD itself is in great shape. It basically operates more or less as it did the day it was bolted onto the spacecraft. As you can see here, though, SHARAD is mounted in a position kind of opposite where all the imagers are on the upper deck of the spacecraft, facing away from the planet. So SHARAD is what we call a facility instrument. It was not competed, and it was produced and provided to MRO by the Italian Space Agency, who operate it through a contract with the University of Rome. We've lost a few of our leaders, unfortunately, over time. Roberto Seo passed away last fall and has been replaced by Pier Francesco Lombardo, also at the Sapienza University of Rome. And of course, I replaced Roger Phillips a number of years ago when he stepped down in prelude to his retirement. And then, I've been involved since 2006. First at Washington University, and then we went to Swery and Boulder in 2007. And then when I joined PSI in 2016, the SHARAD operations moved with me. So over this 19 years, we've acquired quite a bit of coverage. So this map shows the SHARAD coverage at its nominal 3-kilometer Fresnel zone footprint. And the coverage is shown in color in MOLA elevation color. So the black dots are where we don't have coverage at this scale. There's over almost 37,000 observations at this point. The coverage is really dense in some areas, especially the polar regions, but also a number of mid-latitude areas where we have found interesting subsurface features like what are thought to be ices in the mid-latitudes and volcanics or other or some sedimentary deposits in the equatorial regions. So as I mentioned, the SHARAD antenna is attached on a corner of the upper deck of MRO. This is not a best location for the radar. There's interference from the spacecraft body and its appendages, the solar panels and the high gain antenna. And these impact our signal noise ratio. So during normal operations, MRO is often rolled by up to 28 degrees to at least partially compensate for this reduced signal noise ratio. About 1 in 8 of our observations is taken in this manner with a large roll. And at the same time, the solar rays are put in a position that's favorable for SHARAD observing when we're doing so on the night side of the planet, so they don't need to be oriented toward the sun. So here's an example of a radargram from the south polar cap of Mars. The inset map shows the ground trajectory below the spacecraft. And then we get these sort of profile views into the of the surface and the subsurface reflections below the spacecraft along that ground track. And you can see kind of somewhat faintly the layering within the South Pole, South Polar ices shown here on this normal 0-degree roll observation. Then when we go to one of these larger rolls on the order of 25 degrees or so, you can see how the signal gets boosted up quite a bit, and you have a little more clarity in following where these layers are. So that's great. We're happy that we're able to do this on a lot of our observations to improve our signal noise and get a better view of the subsurface. So we've known all along that still larger roll would be helpful, but we didn't really have that well quantified because it wasn't thought in the early part of the mission that we would ever be able to go beyond 30 degrees for these observations. But that possibility has been kicked around for a number of years, and a group in Italy did some modeling work with updated information about the spacecraft and demonstrated that, in fact, if we do go to very large rolls, we can get a substantial increase in the signal noise. So this graphic shows the MRO in its normal orientation with nadir in the Z direction. That's at a 0-degree roll. And as you roll the spacecraft, this is the effective improvement in the gain of the antenna. And you see that out in this direction, where the red is on this torus, we get a substantial improvement in that gain. And then this alternative view shows it more quantitatively. We see that we can get up to nearly 5 dB improvement in the one-way gain, which translates to about 10 dB improvement in the two-way gain for our observations. So this is very exciting. and we presented this to the MRO project and said, hey, we should try this and see if we really get this much signal improvement by rolling the spacecraft almost completely over 120 degrees. And let's see what we get. So here's just another view of what that looks like. Here's our normal kind of nadir looking operation relative to the Mars surface. And here's with that 120-degree roll, basically we're moving the whole spacecraft body out of the way of the antenna. So the antenna has a free view of the surface. And so we were finally able to pull this off in May of 2023. This is our first one of these very large roll 120-degree observation results. The target was this area called Eumenides dorsum, which is part of the larger Medusa fossae materials on Mars. These are thought to be predominantly volcanic ashfall deposits that may or may not have some ice in them. So if you compare to a 0-degree rollover, more or less the same ground track here, you see the dramatic improvement in our ability to resolve the bottom of this material, this mound of materials. So this is the basal return from about 800 meters through this material, which before we really couldn't see it at quite that depth. And you'll notice just in general that the signal is much improved everywhere, and not just in this target area. It's important to note that we're only doing these very large rolls on the night side of the planet. The night side is favorable for SHARAD observing because it minimizes ionospheric interferences, and it also has less impact on the other instruments that are trying to see the surface mostly in the daytime. So to look at this somewhat quantitatively, we can assess the power of the return at that surface, and look at a kind of a histogram view here of the surface return power for the two different observations. And we see that we do, in fact, get almost a 10 dB improvement in the signal noise ratio here between these two observations. So we were lucky enough to acquire another one of these very large roll observations on August 8th of 2023. And in this case, we were able to do it in the South Polar region. So this map now is showing us where we acquired this SHARAD observation. But the radiogram I'm showing you here is actually from a different orbiter, a different instrument, the Mars radar, which has a much coarser vertical resolution, but has greater depth of penetration than SHARAD. As many of you probably heard about, a number of years ago, Mars was finding these really strong basal reflections from the South Pole. They're so strong, they're actually stronger than the surface return in power. And one explanation that was put forward by the Mars team is that these might be subglacial lakes underneath the polar cap. About 20 kilometers across is the size of the feature as they mapped it. So we were wanting to hit this with our observation, but things didn't line up quite right, and we weren't able to go exactly over it, but we did cross very close to it. Normally, the SHARAD signals, even at the the larger roll angles on the order 25 degrees cannot penetrate down to this level. The signal basically is lost about half a kilometer above this level. So that's what's shown here is this 0-degree roll observation from SHARAD. We see this sort of signal peters out about here, but this is not where the base of the ice is. We see a kind of a hint of a basal return here, dipping down below this area. And we know this is in the general area of the basal return because we compare it to the delay time from Marsus, which clearly does see the base. Well, so when we did this 120-degree roll, again, we got a huge boost in the signal noise. And we are, in fact, now getting penetration down to this level, including down at the base, very close to where this Marsus putative lake is. So this is very exciting. We're able to get penetration down there now. So we'll come back later and actually take an observation across the lake feature. So again, if we do the quantitative assessment here of the power of the signal return versus for the 0 roll case versus the 120-degree roll case, we see this big boost in the signal noise. In this case, it's over 10, almost 12 dB improvement in the signal noise ratio. So as I noted earlier, our coverage is really dense in the polar regions. So we actually have a whole bunch of coverage that is very closely spaced here. So we can do a comparison at various different roll angles to see how the improvement goes. And at least for this south polar case, when we compare observations at various different roll angles, we note that the improvement between 0 and 20-degree roll is pretty minimal. There's not really a discernible difference in this signal noise at a 0 roll versus a 20-degree roll. But when we start going above 20 up to 24, then we see a pretty good jump here. And then another much even higher jump when we go to the 120-degree roll. So this is, showing that this maneuver is really paying off. So we tried this again in September of last year, and again back in the mid-latitude area. In this case, we crossed kind of more of a volcanic plain area known as Amazonas Planitia. And so these are thought to be volcanic deposits. And one of the interesting things that we see in this area in our normal observing is we have these dipping, shallow dipping reflectors that sort of peter out and we lose them as you go to the north. North is to the left in these observations. And so we were thinking that with a very large roll, we should be able to follow this thing much more clearly as it goes off to the north. And the interesting result here is when we did the 120-degree roll, we definitely got a lot more clarity in the imaging of this subsurface reflector, but it actually peters out at about the same level. So the question is still remaining, what's going on here? Is there something in this material that's severely attenuating the signal, even when we have a 14 dB boost in this case? Or is this actually the end of the interface? And maybe this interface actually does stop here. So we don't really have an answer to that yet. Maybe further analysis will help us figure that out. But as I mentioned, yeah, okay, I exaggerated a little. This is only a 13 dB improvement in the signal noise here, which is pretty outstanding. So finally, in Memorial Day this year, we were able to come back to the South Pole again. We had to wait for the seasons to come back around 2 years later, because we can only, as I said, we can only do this at night. And the pole is only in darkness during the southern winter. This time we got lucky and we were able to hit that blue spot head on, and get an observation right over the top of the putative Marsus lake. And again, we see these faint reflectors down at depth, where that basal return is, with the attendant improvement in the signal noise and all the material above it. Of course, you may notice that we're not getting a really strong reflection down here. It's actually quite similar to the previous very large roll where we got a faint reflection down at that base. So this is very interesting, and it may speak to alternative interpretations of the material properties down at the base. I won't get into that too much more. We actually have a manuscript in progress right now that Gareth Morgan is leading to assess this result and put it in the context with the other result from our other very large roll and what it says about the Marsus zone of high reflection. So I'll wrap it up there. Basically, these very large rolls are giving us a huge boost in our signal, much clearer looks into the subsurface, often much deeper penetration depth. These enigmatic weak returns from the base open up some interesting questions about the Marsus interpretation of their very strong reflections. We were also training our plans on other locations for applying the same technique. There's a number of debris-covered glaciers in the mid-latitudes in areas known as Deuter and Ilus and Eastern Hellas, the rim of the Eastern Hellas impact basin, that we would like to train this on. There's other stacks of volcanics and sedimentary deposits in both Elysium, Planitia, and Meridiani Planum. And then there's the potential for some deep water ice in that Medusa fossae material that we hit that mound on. So we'd like to train this method on some other areas of Medusa fossae to see if we can tease that out. I think that's the end of it. There's a lot more information about MRO and SHARAD on our website, sharad.psi.edu. Also, all of the references that I talk about in here are part of a database of MRO publications that we maintain at PSI called the mropd.psi.edu. So I'll stop there, and I'm happy to entertain any questions.
Yeah, I don't know if you can see my hand. I put my hand up.
Yeah, go ahead, Isaac.
Yeah, it's really amazing that you get the project to do this and it's working out so well. I'm wondering, so the South Pole was really interesting. Kuller and Plout a few years ago published a map where a lot of places where the basal reflection is stronger than the surface reflection.
Yeah.
I'm wondering, is there any, it might be easier to penetrate to the bottom of those places, especially if they're thinner or it's not as, what do you call it? There's not the waterfall or the fog.
Mm-hmm.
Have you talked about doing that?
There has been discussion of that. We're really focused on getting this Memorial Day observation right over the putative lake. That was the top priority. And now that we have that, yeah, I think the next time the South Pole comes around in a couple of years, I think we want to aim to perhaps target some of those other detections, because I think that could be very helpful in shedding more light on the cause of these strong reflections. I mean, there's been, as you've participated in, there's been a lot of debate over these materials and whether they really can be water or not, liquid water. We gotta have some explanation for why they're getting these super strong reflections. And I think a lot of additional analysis needs to be done both with the MARSIS and the SHARAD data to try to figure that out.
I do think there are several credible and plausible explanations for the bright reflections. And so, that makes it certainly less tenable to just like say it has to be water. But that's a different argument.
Yeah.
I have a question. And thank you, very nice presentation. I was wondering about the potential detection of water ice in Valles Marineris based on epithermal neutrons, if there are any plans to look at that region, and if it's possible.
It's possible that we would make an effort to do that. We already do have a substantial amount of SHARAD coverage there. The real difficulty, though, is even with this boosted signal to noise, we don't get any improvement in the vertical resolution, right? So any kind of neutron detection of hydrogen is going to be confined to the upper meter and really the upper half meter. And that's, we cannot resolve anything at that level. Our vertical, notional vertical resolution is 15 meters in free space. We get slight improvement in the subsurface, although some of that gets traded away in trying to, in the processing, to try to suppress things like side lobes of the reflectors. So there's just no hope of trying to resolve a meter scale feature with SHARAD. Now, if there is ice there and it's connected to a thicker, layer of ice, then we may be able to say something about that. I don't know that the very large roll would be helping much in that realm, because it would have to be within the upper few tens of meters. We do already have a bunch of SHARAD coverage over Valles Marineris, courtesy of Isaac Smith, actually, who was studying some other features that are up on the rim. But the observations aren't confined to the rim; they cross those features in the middle, and people have spent time looking at the observations and not really finding much in those mounds. It's also difficult because of the topography, and there's an awful lot of clutter going on. So even if you think you see something in the subsurface, it may turn out to be a clutter signal from the walls or other slopes within the Valles Marineris area.
So if there is an ice deposit, approximately how thick would have to be unambiguously detectable with this new SHARAD technique?
Just for SHARAD detection in general, it would have to be at least 20 meters deep. The base of it, if we're going to detect the base of the ice. If they're actually seeing the top of the ice, we're not going to see that, right? It could affect the power of the surface reflection, and some assessment of the surface power could point to the possibility of there being ice, but it's not going to be a clear detection of it. If we see a reflector down below in the tens of meters range, then that may or may not be indicative of basal ice. And there are, of course, in the further to the north, all across Arcadia and other areas, we see these faint reflections at the 30 to 100 meter depth or so that have been interpreted to be the base of the ground ices.
Okay, thank you.
Sure. And I think to justify doing a very large roll over this, we would have to see at least some hint of something in the kind of the standard rolled observations.
I see.
So far, no one has actually delved into that data in detail to try to tease something out of it. I mean, I personally looked at a bunch of observations when that detection was first published to see if I could find anything, and I wasn't finding anything, and not from lack of coverage.
I have a question.
Hi, Oz.
Hey, yeah, really interesting stuff with the basal layers in the SPLD. I'm curious about how the dB gain scales with depth through the deposit. So does it apply? So do you get any gain in the upper 500 meters to 1 kilometer when you roll it over? Like how does it work, or is it like focused on the deepest results?
No, I mean, you see this comparison here.
Yeah. Okay.
We get a huge boost in the signal.
Okay.
So, the gain measurement that we're doing is based on the surface return.
Okay.
But you can see just by
Right.
examining these that are scaled the same,
Yeah.
that there's a huge boost in all of these in the signal noise all the way through the stack of layers.
Right. And so then to follow up, my question is, I guess my real question then is, for the widespread so-called fog in the upper 500 meters or so,
Yeah.
throughout the SPLD, like, are you confirming that it's like that there don't seem to be any layers in those? I mean, it's like 80% of the SPLD, right? Like the upper 500 meters don't show any real layering. Is that consistent?
Yeah, well, I'm not sure if that's 80% is the right number, but yeah, there's a lot of this stuff here, right? That
Yeah.
We call a low reflectivity zone,
Right.
or sometimes referred to as reflection-free zones.
Right.
They're pretty pervasive across the SPLD. And you'll see here, there's a faint reflector visible here and also over here, that you don't really tease out well in the zero roll case.
Right.
So it is helping to kind of better resolve that. But apart from that one reflector in there, I think we are kind of confirming that there's not much in the in terms of reflectivity or layers of reflectivity in these zones.
So I
It
mean,
doesn't quite answer exactly why that is.
right. But I mean, it suggests a different like type or style of deposition recently in SPLD,
Absolutely.
right? Because the
Right.
bottom part, that bottom part looks very NPLD-like, right?
Yeah, where the finely layered stack. Yeah,
Yeah.
that is very reminiscent of the MPLD and probably does
Yeah.
at least suggest a similar type of deposition.
Right.
So yeah, I guess one of the theories about these low reflectivity zones is that they were laid down in times of very low dust content in the atmosphere, so you basically aren't getting any contrast between the ice layers that were put down at that time.
And
Right.
maybe also just a long period with high dust, it doesn't vary much, right?
Yeah, Right, and so, well, one outstanding question that people have been poking at is what causes the reflections, right? Is it just variations in the dust content between the layers, or are they actually lag deposits where there's been a kind of a freeze thaw cycle where you've sublimated a bunch of ice and created a lag of highly concentrated lithics that produces the reflections? So yeah, so depending on your model for how the ice is being laid down and whether or not there is a period of sublimation between this layer and the next layer could affect whether or not you get a reflection.
Right.
The other thing I think is interesting is these low reflectivity zones out here in this periphery are potentially, water ice deposits, but they're in a similar geographic or stratigraphic position to the known massive CO2 ice deposits that are up on this very high standing area of the South Pole. So if those were laid down in a similar time period, that suggests that we're in a period of atmospheric collapse, which then may support the idea that they have low dust content.
Right.
Whether or not they're truly water ice or not.
Yeah, it'd be kind of ironic if the SPLD had the lowest ice content. I'm sorry, lowest dust content layer of the two PLD, considering what it
I
looks
mean,
like.
I think in bulk, it's likely to have much higher.
Right.
Just
But
the overall attenuation of the signal and
yeah. No. I mean, it makes
and the
sense. It'd
phase,
just
yeah.
be funny. Yeah, this is really an amazing, this 120-degree roll image it's really amazing, I hope it makes the cover or something for you because it's really a lot to it.
Yeah, we'll see. We're submitting it to GRL,
Nice.
and they may be interested in that.
Yeah. Okay, great. Thanks.
Thank you.
All right, does anybody have any more questions? Awesome. Well, thank you so much, Stan, for the presentation. And thank you everybody for attending.
Sure. Thank you.
Thanks, Dan. Bye.